Welcome to Chapter 8, Intro to Metabolism and Gibbs Free Energy part. So this is Chapter 8, Part 1. We are getting ready for the second part of Chapter 8 to discuss enzymes. So let's get started. We're going to start with metabolism. And a great way to get started with metabolism is to check out this video, Metabolism Stated Clearly. I'll put it in the description so that you can access it really clearly. And it'll give you a good idea of what we're talking about before we get started, before we jump into metabolism. But for a quick breakdown of it, metabolism is the building up and the breaking down of all of the molecules in your body, all of the chemical reactions. And so we break down, or we categorize our metabolism into two different categories. One is anabolism, which is the building up of molecules. So we are making molecules bigger. So if you're taking two molecules and you're bonding them together, that is anabolism. You are building up. Whereas catabolism is the breaking down of molecules. So if you have one molecule, you will be separating it, and that is catabolism. And so when you put all of the anabolism and catabolism in the body together, that makes up your metabolism. And here, all of the chemical reactions in our body happen in metabolic pathways. And so let's look at an example of a metabolic pathway. If we were to eat a potato and get some starch into our system, what we're first going to do is break down that starch. We are going to catabolize that starch into glucose molecules. And so here's our starting molecule, a starch. And an enzyme is going to break down the starch into glucose molecules. It's going to catabolize it. And so here are our second set of molecules. And so that glucose, some of it is going to be burned for energy, and some of it is going to be converted into glycogen reserves, stored in our liver and in our muscles in case we need quick energy. And so an enzyme is then going to anabolize those molecules and make glycogen reserves. It is a few more steps than this to get to these points, but I'm hoping that you are getting this understanding that we have molecules and enzymes are going to be doing the jobs of breaking things down and building them up. And we have these steps, reactions of molecules as they change from A to B to C to D. And so that is an understanding or a breakdown of our metabolism. And in order to continue understanding metabolism and enzymes, we need to have a more firm understanding of thermodynamics. Thermodynamics is simply the study of heat flow into and out of a system. And so we have two types of systems, cold systems, open systems, and closed systems. If we look at this mug here, we're going to imagine that this mug is in a perfect vacuum, sealed container, and no heat can go in and no matter can go in or out. So if we put hot coffee in here, it will forever be hot because energy cannot be lost. It cannot be lost to the environment. However, here in this open system, there is energy and matter is being transferred into and out of the system. This coffee mug is losing heat, and potentially there's dust and bacteria falling into the coffee. And so organisms are far more closely similar to the open system. We are open systems. And so being an open system, we are guided by the laws of thermodynamics. The first law of thermodynamics is that energy can be transferred, it can be transformed, but it cannot be created or destroyed. So it's the conservation of energy. And so let's look at a couple of examples. We have chemical energy here in this food. And so this little boy is going to eat the ice cream cone, and we're going to convert that energy, that chemical energy, into kinetic energy. It's going to help us move around. It's going to help us think. So that's going to be converted. It's not lost. It doesn't just disappear. It's converted. Another example is this light energy from the sun is going to be converted into chemical energy by the chloroplasts in this leaf in the process of photosynthesis. So that light energy is going to be converted into chemical energy stored in the bonds of glucose. So that's the first law of thermodynamics. Our second law of thermodynamics is entropy. It's for every energy transfer, in the universe increases entropy of the universe, which is tough to wrap your head around. But everything is moving towards increasing entropy or disorder. The universe is expanding. The universe is increasing in entropy. It is an unstoppable trend towards randomization. And so it is simply, as we are talking about entropy, it is a measure of how dispersed the energy of a system is amongst the way that the system can contain the energy. Let's break that down. If we were to look at this beaker A and all the molecules in here, and we were to compare it to beaker B has reached equilibrium. There's less energy in this system. It is more disorganized. But there are fewer ways in this system to organize the molecules or for the energy to be dispersed. So if we were to take this molecule, it can be here. This molecule could move here. It can move here. It can be here. But in this system, there is more ways to arrange the energy. So if you take this molecule, sure, it can be here, it can be here, it can be here, but it can also be here, and it can be here, and it can be here. So there's a lot more opportunity for each of these molecules to be in different spaces, for the energy to be arranged in different ways. And so therefore, as we reach equilibrium, as we take up more space, we are moving towards entropy or less organization of the system. And so in thermodynamics, if a process can proceed or a chemical reaction can proceed without an input of energy, we call this a spontaneous reaction. This is energetically favorable. So let's think of a downhill process. If you were to roll a ball down a hill, it will proceed. You drop the ball, it will proceed, and the ball will roll down the hill. There is no need to put more energy into that system. It is going to proceed. So spontaneous is not necessarily a quick reaction. If we think about metal rusting over time, that is a spontaneous and slow reaction. Another example is hydrogen peroxide. It will break down into water and oxygen all by itself without an input of energy. That is a spontaneous reaction and is going from one piece to two pieces. And so therefore, it is moving towards entropy. So it is spontaneous and moving towards entropy. So let's look at our molecules here. Hydrogen peroxide. If we have one hydrogen peroxide molecule, let's just look at one molecule, and we break it down into a water and an oxygen. You went from one piece to two pieces. That is increasing entropy because there are more ways for these two molecules to be arranged. And so therefore, they are moving towards entropy. And this process is spontaneous because it's going to happen on its own. I don't need to add heat to this scenario in order to break down hydrogen peroxide. A counterintuitive example of a spontaneous process in biology is the formation of micelles or lipid membranes. This may seem like it's moving towards more organization because the phospholipids or the lipids are going to hide their tails towards one another, and the phosphates are going to interact with the water. So this is going to happen spontaneously without an input of energy because the nonpolar and polar molecules don't react together. So you can say, I'm sure you're thinking, yes, but that seems more organized. Well, we have to think about this system, the system of phospholipids, but also the system around it. Is there, including the system around it, so in the water where these lipids are, we have created more disorganization of the water around the lipids in order to create this organized state. And so if you include the entire system, the phospholipids and the water, it is in fact moving towards increasing entropy or increasing disorganization. Like I said, that's a counterintuitive example, but it's a famous one in biology, that the formation of the lipid membrane is in fact spontaneous. It happens on its own without the input of energy. And so organisms are islands of low entropy. So we are not breaking down, we're not falling apart. We are islands of low entropy in an increasingly random universe. But in order to maintain our low entropy, so that we don't fall apart, so that we don't become disorganized, we are taking energy from the systems around us in order to maintain our low entropy. And so we are actually, by taking the energy from the systems around us, we are creating more disorganization in the world around us. So we use glucose for energy. And that is, the glucose is filled with the energy from the sun. We squeeze the energy out of glucose to fuel our requirements of low entropy, of not falling apart, to maintain the characteristics of life through cell respiration. And so we strip it of its energy, and we take glucose, and then we produce carbon dioxide and water, 2 molecules with very little energy. So we take the energy and we are creating 2 molecules, increasing entropy, and we're taking the energy to do this. And so therefore, we are creating entropy in the world around us in order to maintain our low entropy. That's kind of a lot to take, so take an intermission, take a deep breath, get a drink of water, and come back. And we'll start with the Gibbs free energy equation. So Gibbs free energy is a little intimidating at first, but once you wrap your head around it, it's not so bad and it makes a lot of sense. It is the mathematical underlay of thermodynamics. It tells us whether a process will be spontaneous or not. Will it happen on its own? And so G, triangle G or delta G, is going to be representative of the words spontaneous or non-spontaneous. If we input numbers into this equation and it gives us a negative G, this means that the process is going to be spontaneous, also known as exergonic, meaning that the process is going to be giving out energy. So think of a candle burning. As you light a candle on fire, you create the chemical reaction, and then it proceeds on its own. And it doesn't need any more input, and it is giving energy to the world around you. It is warming your hands. It is giving energy to the system around it, to the environment. Whereas a positive G is a different story. This is endergonic or non-spontaneous. These 2 words are going to be used synonymously, endergonic, non-spontaneous. And if you were to put some baking soda and vinegar into a bag, which I recommend that you do, and you put that on your hand, you'll feel a chemical reaction. It's cold, and it feels cold because what's happening is, in order for that process, the explosion, right, the fizz of baking soda and vinegar to occur, it needs energy from the system and from the environment around it. And so it's taking energy. So if you put that bag on your hand, it feels cold. And so in order for that chemical reaction to continue happening, it needs energy. And so therefore it is endergonic, or it is non-spontaneous. And so that's represented by a positive G. So a change in free energy, delta G is a change in free energy, or the available energy. And so remember that the words spontaneous or non-spontaneous are synonymous with exergonic or endergonic. And so a negative G is answering the question, is the system losing energy? Is it giving off energy? And a positive G is the system requiring energy from the environment in order for the reaction to occur? So let's look at delta H. This represents enthalpy. Enthalpy or the change in enthalpy. This is the total amount of energy in the system. And so we're going to use words to describe enthalpy, exothermic or endothermic. So if something is exothermic, it is giving energy to the system. It is giving energy out. So once again, let's think about the candle burning. It is giving off energy. And so therefore, that is exothermic. Whereas if we look at the baking soda and the vinegar, it is taking energy from the system. And so therefore, it is endothermic. And so this is the energy of the system, the total energy of the system. How much energy is in that candle? How much energy is in that bag of baking soda and vinegar? The T is temperature in Kelvin, and delta S is a change in entropy. Is the system increasing in disorder or is it decreasing in disorder? So think about it like this. If change in H is the total energy in the system, so this is the total energy in the system, we're simply adding or subtracting from the total energy in the system. It is the system losing or gaining? So if it is losing energy, it is going to become negative. It'll make G negative and spontaneous. If it is gaining energy, if this is going to increase, so if this is a negative, so if you're going to subtract a negative number, you're going to add, and so therefore that'll make G positive. If the system is becoming positive, if it's at a positive G, then it is non-spontaneous, or it is endergonic. We will use this more, so if this is confusing, don't worry, stick with it. So the example of negative G is a candle burning. So let's look at this. The enthalpy, or the change in enthalpy, the total energy or the wick of the candle is becoming less because it is being released as light and heat. And so therefore it's going to be exothermic. The T, change in S, or the entropy, before the candle is burned, all the elements are in a confined area. They're in the wick. And so after the candle is burned, the elements are more dispersed. They are more disorganized. It is moving towards entropy. And so it is becoming more disorganized, less energy in the system, and it is spontaneous. So that's going to give us a negative G. In the process of cell respiration, notice entropy increases. S, the number of pieces in the system increases. So if this is cell respiration, we start with glucose and we have some oxygen, and then we break it down and entropy increases. We have water, we have C6, we have 6 CO2, 6 H2O. So we have 6 carbon dioxides, 6 waters. We started off with 1 carbohydrate and 6 oxygen, and here we are with 12 molecules and ATP. And so that is entropy is increased. Enthalpy has been released from the bonds of glucose. And so therefore, this is an exergonic process. So, this is going to be an exothermic process, which you can feel on your forehead, that the heat is being released as we break down sugar. And so because we have an increase of entropy and an increase of enthalpy, this is an exergonic process. It'll be negative G. The delta G, is negative 686 kilocalories per mole in a standard condition of 25 degrees Celsius and in a pH of 7. And think of this, if you were to work out in the heat, the T, or the temperature, your rate of respiration will increase and you will shunt more heat, and that's going to increase the disorder in the system even more. Let's look at the reverse of this. In the process of photosynthesis, notice that entropy decreased, S decreased. So here we started with 6 CO2, 6 H2O. The number of pieces in the system decreased. We went from 12 to 1 big glucose molecules and some oxygen. Also, enthalpy decreased because we trapped light energy into the bonds of glucose. And so this is an endergonic process. I made a little mistake. The enthalpy increased because energy was trapped into the bonds of glucose. The enthalpy increased. And so this is an endergonic process. Baking soda, just like the baking soda in vinegar. And so we're going to have this, if we were to put all of the numbers into the equation for Gibbs free energy, we would come out with, this is not a coincidence, positive 686, just the opposite of cell respiration, positive 686 kilocalories per mole in standard conditions of 25 degrees Celsius and a pH of 7. So an exergonic reaction, also known as spontaneous, and the reactants have more energy than the products. So if we look at this graph, or this graph here, then free energy is on the y-axis and the progress of the reaction is on the x-axis. We can see that the reactants have more energy. Energy is released, so therefore the products have less energy. The amount of energy was released. This is an exergonic reaction. It is spontaneous. Endergonic reaction is the opposite. Energy is required. It is non-spontaneous. So we can see that the reactants gained energy and the products have more. And so this is it. Please feel free to ask questions and we will be working on the POGL together. Have a great day.